Welcome to Brain Vision.
For our question, we are asked to see figure 51, which shows a specific case for n equals 6, but we just want a general expression for n being any side of a polygon, so any n-sided polygon. So for part A, it says determine the magnetic field at the center, okay? And then I also drew out a little diagram here real nicely in paint to kind of show you where the center is relative to the polygon. So the polygon has a side length of L, which we can break in half. And therefore, the distances of the different sides, we have r, y naught, and then the other side would just be L over 2 there. And the angle would be pi over n, where n is the number of sides of the polygon. Okay, so for part A, to determine the magnetic field at the center of the polygon, we have to first determine the magnetic field due to the finite wire, which is just the one side here. So to start, we can use the Biot-Sievart law. So we have B here, the magnetic field, is equal to mu naught times I, the current, times y naught, which is labeled in the graph, divided by 4 pi. And then we're going to take the integral of dx prime divided by x prime squared plus y naught squared, all raised to the 3/2. Okay. Well, you could use like a standard integral here, or what I would recommend doing is you could look this up in an integral table, because this is a little bit more of a tricky integral. You could try some other different integration methods, but I just looked it up in an integral table. And so what I found was this integral here. Oh, and by the way, what are we integrating over? We're integrating from minus L over 2 to L over 2, because each side there of that polygon is broken into length L, but we break it in half, because y naught is the distance from the halfway point all the way to the origin. So we're breaking it in half to get this right triangle here. So we go ahead and carry out that integral by using an integration table. So we still have our constants out front. We have mu naught times I times mu naught times I times y naught divided by 4 pi. And then the integration table gives us the value 2 times L, because remember we plug in minus L over 2 and L over 2, divided by y naught squared times y naught squared times the square root of L squared plus y naught squared. So we can do a little bit of simplifying here. This y naught squared, that squared term is going to cancel with that y naught value there. This 2 can cancel with this 4 to simplify that down to a 2. And so what we end up with here, I'll write it on the next page, is that the b equal to the infinite straight wire here is equal to mu naught times I times L divided by 2 pi y naught and then this all gets multiplied by 1 over the square root of L squared plus y naught squared. Okay. But again, that was just the magnetic field due to the finite wire. So now we're going to find the magnetic field of an n-sided polygon using the information that we just found from the finite wire. Well, one thing we can do is we can look at the figure and we can see that, well, obviously in the figure, theta is equal to pi over n. Therefore, using our trigonometric identities, we can see that, we'll just write it over here. We have L over y naught is going to be equal to the tangent of the angle theta, which we said was pi over n, or it labeled in the figure as pi over n. Because the tangent of the angle is the opposite, equal to the opposite over the adjacent, where the opposite is L over y naught. Okay. So now that we have that, we can also realize that the value L squared plus y naught squared is just going to be equal to R, right? So R, since it's the hypotenuse, is just going to be equal to the square root of L squared plus y naught squared. Okay. So, so we did make a mistake over here. I said that we're going to integrate over the range of L over 2, but we're integrating from minus L to L because we start at the origin point. So I don't know if anybody caught that or not, but if you notice that we're using L, not L over 2 for all of these, it's because if you look at this distance, we start at 0 and we go L to the right or L to the left. We're just considering one of those. So there was a little typo there, but that's easily fixed. And you might have caught that when you did the integration anyways. Okay, so now we have these new values for L over y naught, which shows up in our B equation. And we also have a new value for L squared plus y naught squared. So we can go ahead and put these in, and we find that B here is equal to mu naught times I over 2 times pi times r, because I just replaced the L squared plus y naught squared with r. And now I'm going to replace L over y naught in the equation above with tangent of the angle pi over n. But that's just for the one side. We just did all of this for one side. And we want to consider this in general for an insided polygon. So the net for an insided polygon, we'll call this B sub n, is going to be equal to the total number of sides, n, times what we just found above. So this is going to be n times mu naught times I over 2 times pi times r, all times the tangent of the angle pi over n. Okay, and that can go ahead and be boxed in as our solution for part A, because that's what we were asked to find in part A, was the magnetic field at the center from the insided polygon. Okay, now for part B, we'll start a new page. We are asked if n is allowed to become very large, i.e. n goes to infinity, show that the formula in part A reduces to that for a circular loop, which makes sense. If you just keep adding infinite n's, eventually this thing becomes so circular that it ends up being approximately a complete circle. So how can we show this? Well, we're going to use that tangent of the angle to show this, because the tangent of pi over n has that n value in it. Well, what if we let n go to infinity? This would be the tangent of a very, very small number. So as n goes to infinity, this becomes pi over n. We can say as n goes to infinity. Okay. So if we let pi over n, or tangent of pi over n, go to pi over n, and just plug that into our equation for the net magnetic field, B sub n, what we have here is n, and this was multiplied by mu naught times I divided by 2 pi r. And then now, instead of being multiplied by the tangent of pi over n, it's just multiplied by pi over n. So what we can see is that a couple of things are going to cancel here, right? We have this n term on the bottom that's going to cancel with this n term over here. We have this pi term on the top, which cancels with this pi term in the denominator. So we can rewrite this as mu naught times I divided by 2r. But that's the magnetic field for a circle, so we proved it. So we can say, which is the same as the B field for a circle. And we can go ahead and box that in as our solution for part B, which is the final part of our question. Now, let's go ahead and indicate this as part B over here too.